All right, hello everyone, and welcome to lesson 4.4, which is on elementary reactions, in unit 5, which is on kinetics. Today we are focusing on elementary reactions, which occur in a single step at the molecular level. For these reactions, the rate law can be written directly from the balanced chemical equation because the coefficients represent the actual particles involved in a collision. The lesson also emphasizes that reactions requiring simultaneous collisions of 3 or more particles are rare, helping explain why most elementary reactions involve only 1 or 2 reactants. An elementary reaction is a single step with an overall reaction mechanism. Although a balanced chemical equation may show multiple reactants colliding at once, it's extremely unlikely for 3 particles to collide simultaneously with the correct orientation and energy. So for example, if we look at the reaction 2NO plus O2 reacts to form 2NO2, it appears to involve 3 particles, but in reality, it occurs through multiple steps. So each step is called an elementary reaction involving 1 or 2 particles, which makes the process physically realistic and consistent with collision theory. So even though when we are given this overall reaction, it suggests that all of the collisions kind of happen at once, that's not actually the case. Instead, it happens through a 2 mechanism made up of 2 elementary reactions. In the first step, 2 NO molecules collide to form an unstable intermediate. Notice that this intermediate N2O2 is not found in our overall reaction because in the next elementary step, that intermediate is used up to form our product, which is in our overall reaction. When those 2 steps are added together, the intermediate cancels out, leaving the overall balanced equation 2NO plus O2 reacts to form 2NO2. This shows how complex reactions proceed through simpler, physically realistic steps rather than a single multi-particle collision. When a reaction mechanism is given, each equation represents an elementary step. An intermediate is the species that is produced in one step and consumed in another, so it does not appear in the overall reaction. In this mechanism, N2O2 is our intermediate because it is formed when 2 NO molecules react and then used up when it reacts with oxygen gas to form our product 2NO2. Recognizing those intermediates is important because it helps explain how the reaction proceeds step by step and are canceled out when determining the net reaction. So now that we kind of understand the basis of reaction mechanisms and elementary reactions, let's talk about one of the most important parts of the mechanism, which is the rate determining step. So what that means is it is the slowest part of the reaction. So let's put this into non-chemistry terms. Let's say you were making chocolate. If you're making chocolate and it takes 15 minutes to make the chocolate, then it takes 8 hours to cool it, and then it takes about 5 minutes to package. The step that is limiting you the most when you're making this chocolate is going to be your cooling time, which is 8 hours. Speeding up the production of it or speeding up the packaging is not actually going to significantly change how quickly the process goes because cooling it takes so long in that process. That is exactly what we're talking about in this rate determining step. The rate determining step is the slowest step in the reaction mechanism and controls how fast the overall reaction proceeds. Because all other steps must wait for this slow step to occur, the rate law for the entire reaction is based on the stoichiometry of the rate determining step. And you find that by looking at whichever elementary step is labeled as slow. That is your rate determining step. In the example shown, the first step is slow and involves 2 particles of A colliding to form B. Since this step limits the reaction, the rate law is going to depend only on the reactants in that step, giving you a rate law of rate equals K with the concentration of A squared because it's second order. This means that the reaction is second order because two particles of A are involved in the rate determining collision. If the slow step is not the first step, you have to combine all of your elementary steps up to and including the slow step, and then you have to eliminate your intermediates. So in this mechanism shown, the first step forms an intermediate and is fast, while the second step is slow and involves the intermediate reacting with C. Because the intermediate was formed from two A particles in the earlier step, the overall rate law must include both A and C, which leads to our rate law, rate equals K with the concentration of A squared times the concentration of C. And you'll notice that A is second order because there are two reacting A particles in the first elementary step, and then C is first order because there's only one particle of C reacting. So our overall reaction order would be those two added together, which is third order. This example says, given the following elementary steps, what is the intermediate, the overall reaction, and what is the rate law if elementary step was the rate determining step? So first, it wants us to look for the intermediate. Remember, the intermediate is the species that is formed in one step and consumed in the other. And we can see that H2I2 was formed in step number 1 and then consumed in step number 2. So the intermediate is H2I2. The next part of this question says, what is the overall reaction? So the overall reaction is just going to be canceling out those intermediates. So our overall reaction is 2HI forms H2 plus I2. And now it says, what is the rate law if elementary step 1 is the rate determining step? So because the first step is our slow or rate determining step, we're only using that first step in our rate law. And remember, with rate law, we're only using our reactants. So whenever it asks you for rate law, you're starting with the word rate. Rate equals K, and then our reactants. In this case, we have HI as our only reactant. And since there are two of them, it's going to be raised to the second power or second order. Gaseous cyclobutene breaks into two gaseous ethylene molecules via a single-step unimolecular reaction. Write the balanced equation for this reaction and then write the rate law for the reaction based on the stoichiometry of the elementary step. So this is essentially telling you that there's only one elementary step in this reaction mechanism. So that single step is going to be the rate determining step because there is only one. So first part of the question is to write the balanced equation. So we know we are starting with gaseous C4H8. And we are converting that into two ethylene molecules, which is C2H4, and it was also mentioned that it was gaseous. So this is our balanced equation, and then it says to write the rate law. So remember, whenever it says rate law, we are writing the word rate. That's going to be equal to K times the concentration of your reactants, which in this case we only have one, C4H8. And since we only have one of those particles, it is first order. All right, so here we have two elementary steps in our reaction mechanism. It says what is the overall chemical equation and what is the rate law for specifically elementary step number 2. So first we need to find the overall reaction by adding the two elementary steps and canceling out any intermediates which appear on both sides. So our intermediate here is going to be HI because it is formed in step number 1 and then consumed in step number 2. So now when we want to get our total reaction, we're just going to add everything up together. So we have 1 H2, we have 2 ICLs, we have 2 HCl's, and we have 1 I2. So this is our overall reaction. And now it specifically wants the rate law for elementary step 2. Now they can ask for this This wouldn't be the actual rate law for the equation because step number 2 is not the slow reaction, but it's asking for the rate for step number 2, so we're going to give it to them. So just looking at step number 2, we have 2 reacting particles. So that means we are going to have rate equals K times the concentration of HI. There's only one HI particle, so it's first order. And then times the concentration of ICO, which again is only one particle, so it is first order. And that would be the answer to this question. A two-step reaction mechanism is proposed for a gas phase reaction as represented above. What is the chemical equation for step 1 and the rate law for the overall reaction? So in order to get step 1, I'm going to be looking at step 2 and the overall reaction to see what cancels out to give me a clue at what's in step 1. So I'm going to go ahead and start off with my overall reaction. I know I need NO2 as a reactant, and I have NO2 as a product, which means I need an extra one for my step 1 reactant. So I'm going to put 2 NO2 in gaseous form. So when this NO2 gets canceled out, I am left with 1. Then I move on to CO. CO is already a reactant in step 2, so I don't need to put that in step 1. Then I go to NO. I do not have NO in my step 2 reaction at all, so I know that's going to be in my product for step 1. And then CO2. CO2 is already a product in step 2, so I also don't need to react or put that into step 1 for the elementary reaction. Now my final thing, if you can see what is not underlined here, is my intermediate, NO3. So I know that is going to be something that is produced in step 1 and then used up in step 2. So that is NO3 gas, and then that would be our first elementary step. Now, because we know step 1 is our slow or rate determining step, that is going to be how we get the rate law. So whenever it wants rate law, again, we do rate equals K times our reactants concentration. So that is NO2. And since we have 2 of those particles, that is going to be second order. So that is our answer for this question. And then for our last example, it says NO and O2 react to form NO2. The rate law of the reaction is rate equals K NO squared times the concentration of O2. If the reaction occurs in a single elementary step that is a 3-body molecular collision, then which of the following is the equation for the elementary step? So this is a multiple choice question that I turned into a free response question. So let's go ahead and figure that out. So luckily, we know that from the rate constant, that pretty much gives us our reactants and how many of them there are. So we know we have NO gas, and we know we have 2 of them because it's second order. And we also know we have O2 gas, and we only have 1 of them because it's first order. And then we can see from the very first part of this question that we are forming NO2. And then we just need to make sure it is balanced, and it is not, so I'm going to go ahead and put a 2 in front of NO2, and that is our answer. And that's it for lesson 5.4. If you have any questions, please feel free to reach out or leave a comment below. Hope you have a great day. Bye.